Okay, this is Kinetics tutorial question 8. Okay, this question, the focus is on the effect of temperature and catalyst on the rate of reaction. Okay, especially the use of a Boltzmann distribution curve. Okay, we look at this reaction here, H2I2 giving you Hi. Okay, part A is quite straightforward. Okay, what's the order of reaction? We look at the rate equation. Okay, both are power 1, so it's first order with respect to H2 and first order with respect to I2. And the overall order of reaction is 1 plus 1 equals to 2. Okay, part B they want you to draw energy profile diagram. Okay, please be able to distinguish the term energy profile diagram from the term energy level diagram, okay, which are two different things. Do a summary and to sort them out. Okay, what's the difference? Okay, energy profile diagram, this one is quite straightforward. Okay, what I would expect to see in this energy profile diagram is that there should only be one hump. Okay, because this is a one-step reaction. Okay, label your EA, label your delta H, and the two axes, and to include your reactant product right at the correct position. Okay, part C. Okay, part C, given the number of moles of H2I2, volume, and the rate, calculate the rate constant K. Okay, so we use the rate equation, we sub in the value. Okay, but of course in this case, you are not given concentration. Okay, how are you going to input the concentration terms? Okay, concentration will simply be number of moles over the volume. Okay, so this is the concentration of H2. Alright, I sub in, I should be able to get what is the rate constant K. Okay, I trust that you know how to derive the units for the rate constant here. Okay, part 2, how would you expect the rate to change when you change the temperature? Okay, I think it's quite commonsensical that when temperature increases, rate would also increase, right? Okay, the rate constant may not be that obvious. Okay, rate constant is not really a constant, but it's a constant value at a particular temperature. Okay, remember in experiment 6, you encounter this equation, the Arrhenius equation. Okay, when temperature increases, the power becomes smaller. Okay, but this is a negative power. Therefore, K will also increase when T increases. Okay, part 3. Okay, part 3 is a very important question. Okay, part 3 wants you to use a Maxwell-Boltzmann distribution curve to illustrate and after that to explain how the increase in temperature will increase the rate of reaction. Okay, for a temperature curve, I should see two curves. Okay, for temperature representation. Okay, curve 1 is at a higher temperature. Okay, curve 2 is at a lower temperature. Hey, sorry, curve 2 is at a... Okay, I say again, curve 1 is at a lower temperature. Curve 2 is at a higher temperature. Okay, I think the thing you need to remember is that these two curves, they have the same area under the curve. Okay, the area under the curve represents the number of reactant particles. Okay, so for temperature 2, which is at a higher temperature, the curve shifts to have a broader base. So when I have a broader base, the number of particles under the curve that has energy above EA is more because the area is bigger compared to the yellow graph at this point here. Okay, maybe I use another color. Okay, at this point here, this is a smaller area. Okay, some students ask why the two curves have different peak heights. Okay, it has to be because both curves have the same area underneath it, and at a higher temperature, the curve shifts to give a broader base, and hence, therefore, the peak has to come down. Okay, alright, in the drawing, right, take note at the end, the two lines, the two curves do not reach zero, okay, and they will continue on. Okay, and in the explanation, okay, what do we look out for? Okay, we look out for this. When temperature increase, the number of reactant particles with energy above EA increases, and the effective collision, okay, not just effective collision, very important, the frequency of effective collision increases. And since rate of reaction is proportional to the frequency of effective collision, rate increases. Okay, and I want you to contrast, okay, the temperature curve with the catalyst curve soon. Okay, we move on to the next part. Okay, part D. Okay, the above reaction can be catalyzed using platinum metal. Okay, what kind of catalysis is this? Okay, platinum is a metal. The reaction is in gaseous phase. Therefore, platinum metal is a heterogeneous catalyst. Okay, part 2. Part 2 wants you to use a Maxwell-Boltzmann distribution curve to explain why the use of catalyst increases the rate of reaction. Okay, as you can see, there's only one curve, okay, compared to a temperature curve where there are two. Okay, what a catalyst does is that it changes the EA, okay, from an original EA to a new EA. So you see that there are more particles underneath the curve that has energy above EA. Okay, so the explanation would be increasing catalyst increases the rate of reaction by providing an alternative pathway of lower energy, lower activation energy, and hence there are more particles with energy greater than EA. And after that, so be the frequency of effective collision increases, and since rate of reaction is proportional to the frequency of effective collision, rate increases. Okay, for these two kind of graph, I normally will use an analogy. Okay, an analogy for a class of student, okay, to score an A. Okay, what methods can I help student to score A? Okay, I can either increase the temperature, okay, by pushing more student, okay, to score an A, okay, to do well. For example, I can tighten the process. Students who do not submit work will stand outside the class. Okay, many means by increasing the temperature, okay, to help students to study harder and pushing more students to cross the benchmark to score an A. That's one method. Another method is like the catalyst method. I lower the benchmark, okay, from an original 70 mark to score an A, I lower the mark. Maybe I lower to 60. If 60 is an A, then more students will score an A. Okay, so these are two analogies to illustrate to you the concept of increasing temperature and adding catalyst for a rate of reaction to increase. Okay, the last part, drawing an energy profile diagram for catalyzed and uncatalyzed reaction. Okay, I think it's straightforward. For uncatalyzed reaction, EA is higher. Okay, as you can see here, EA is higher. For catalyzed reaction, EA is lower. Alright, and the last part, they ask you what is the activation energy for the reverse reaction for the catalyzed reaction. Okay, if we go backwards, the red color line, okay, the EA is here. Okay, the EA is here. Right? Okay, which is your 106 plus 10. This is 106, this is 10. So I sum them up together. The EA for the reverse reaction will be 116 kilojoule per mole. Okay, so this is question